and we're going to roll some tape. Oh, except you guys need to be able to see it. Share computer sound. Okay, let's try it again. Hello, space fans, and welcome to Professor Britton's Wacky Universe. Last class. All right, hello space fans, and welcome to your final lecture of Astronomy 1010, the solar system. Today we are going to learn about Jovian planets and hopefully Jovian moons on hyperspeed, because I have a lot to cover and only one lecture to do it. On the other hand, it's a fun lecture. Learning about Jovian moons is interesting. Some of them are bigger than the planet Mercury, and many of them have interesting geological activity, which is kind of surprising because if you think about Mercury, Mercury isn't an overly geologically active kind of planet, right? What would you guys say is like the dominant form of geology on Mercury? Do we need to look at a picture? Let's see a picture. Mercury planet. Let's look at a picture from the Messenger spacecraft. Let's go to, oh wait, I keep forgetting to share my screen with you guys. Okay, so let me click on this thing. What is the dominant form of geology on this planet? Jace? Kayla?
Cratering?
Trolls? Oh, sorry. Yeah, Kayla, did you say impact cratering? I think you said that.
Yeah, I did.
A little quiet. Okay, yeah. Impact cratering is the dominant mode of geology. And Mercury is a little bit smaller than the largest moon in our solar system, Jupiter's moon, Ganymede. And, well, it turns out Ganymede has a lot of impact craters too. But there are moons even smaller than Mercury or Ganymede that have a lot of interesting geology. Hey, just as a thought question, what's the second most abundant type of geology? This is a harder question. The second most abundant type of geology on Mercury after impact cratering. We talked about this once. You can see some of the, it's not erosion because there's no atmosphere, Jace. And if there is any,
tectonics?
Yeah, it's kind of like plate tectonics. If you look here, do you see these long, hot, bright scars? You're looking at an aerial photograph here, so they don't look like much. But if you were to stand on the surface of Mercury, these would be long cliff walls. We had a special vocab term for them called scarps, okay, or escarpments. And these would be long cliff walls that run for thousands of kilometers. The origin of these cliff walls on Mercury is actually kind of interesting. Mercury doesn't have an active set of plate tectonics, say the way Earth does, but it does have this stupidly, obnoxiously large metal core. And as all y'all know, metal contracts as a higher rate of thermal contraction than rock does. This is why we put those expansion joints in bridges, especially in the Northeast, where we have these strong temperature fluctuations. The thinking of how Mercury got so many escarpments without an active set of plate tectonics goes something like this. At some point in Mercury's past, it was a much warmer planet, but it had an obnoxiously large share of metal, perhaps because it formed close to the sun, where temperatures were higher. And as the planet rapidly cooled, the interior shrunk so much faster than the surrounding overlying layers of rock that the rock layers had to fold and collapse on themselves, creating these long fold marks or escarpments all over the planet. This is a type of tectonics, but it's a wacky type of tectonics. It's basically the planet folding over on itself and creating these kind of, well, I wouldn't call them stretch marks, I'd call them shrink marks. And we can see them all over the planet. The fact that this escarpment slices through this crater, which probably formed during heavy bombardment, it tells us that the shrinking of Mercury was a later activity that happened after the first billion years of our solar system's history. Okay, so Mercury's got some cool scarps, right? It has slightly more interesting geology than just plain old cratering. But when you look at a picture of Mercury, I mean, let's face it, actually that's the backside of the moon. It's a big cratered rock, okay? There's impact craters all over its surface. And today we would consider it to be geologically dead. No erosion, no volcanism, and some ancient tectonics in the form of scarps, but that's not the same thing as robust plate tectonics. Before we head out into the Jovian world, I think it's best to sort of have a little reveal with you guys here in notes about the fundamental properties of a planet. And I want you guys to keep these in mind as we exit the inner solar system and make our way out into the icy, colder realms of the Jovian planets. In general, there are 3 fundamental properties that determine the evolution of a planet more than any other things from its formation to its eventual appearance today. And these are what we might call the 3 fundamental planetary properties. Now, I've hinted at these as we've gone so far, but I haven't really codified them, so I want to do that. The first fundamental property of a planet, and maybe its most important, is its size. Why don't you guys tell me what you've learned? What factors does the size of a planet affect in terms of its geology or appearance? Or what property of a planet does size affect more than any other thing? I can actually think of 2 things. Can you? Laura, you seem like you want to be called on right now. In fact, you've got a face that's saying, please call on me. I'm dying to participate.
Oh, man. I don't know.
Someone's got to rescue your fellow classmate. Size, but think about it. What have we been talking about all this time?
The inner temperature?
The internal heat. Yes, that's one of the big ones. The internal heat. What geological properties does internal heat most directly affect?
Volcanism?
And?
Plate tectonics?
Yeah. So your volcanism and tectonics are tied to internal heat, which is tied to size. Jace, can you think of one other thing that size might affect? Something that might play into our discussion of atmospheres? And our ability to hold onto an atmosphere?
Gravity.
Yeah, that's right. Gravity matters, of course, for atmospheres. If you have a powerful gravity, you can have a potent atmosphere. And if you're a little dinky planet that can't hold on to its molecules, why then you are destined to be a cratered rock in space. Okay, so we can see the importance of size in our planetary properties. The second, of course, is your distance from the sun. Your distance from the sun affects exactly one property, but it's a big one. Surface temperature. I ain't talking internal temperature. I'm talking surface temperature. And distance from the sun plays a role in whether or not the seedlings that formed your planets contained rock and metal or rock, metal, and ice. It also affects whether your atmospheric particles can be held on or not. Higher temperatures tend to boil away an atmosphere, as you will see in today's epic office hours. You know, this is our last class. We're going to do an office hour after lecture where we solve some tricksy problems. And I'm just going to give you guys one final little squeeze before I let you go, okay? And the third one is one that you wouldn't naturally predict. It's rotation rate. Rotation rate matters a whole lot, more than you'd think. If
I
you
have a
think about the
question.
difference between the way Earth looks today and the way Venus looks today, it can almost entirely be boiled down to rotation rate with just a smidge of distance from the sun. I can think of two things that rotation rate directly affects.
I have a
Can you?
question real quick.
Lucas, ask me your question.
So even though Mercury's surface temperature is warmer than any other planet, it's not enough.
Wait, hold on. What did you say hotter than any other planet?
Or the temperature is higher, the surface temperature, since it's closest to the sun?
Well, we got one small problem, Bob. Where's my lecture on the solar system? Let me just show you a couple slides here. So Mercury has two temperatures, a subsolar temperature on the sunward side of 700 Kelvin and a back nighttime temperature of 100 Kelvin, because without an atmosphere, there's no thermal insulation. It's just, you're either in the sun and you're boiling, well, boiling isn't even the right word here. You're hot enough to melt lead, or you're cold enough to almost freeze nitrogen. Okay, so none of that sounded very good. But
it's not enough heat to add to the internal temperature of the planet at all, because it just goes away at night.
Yeah, and also this is something about the second law of thermodynamics, about entropy, right? The sunlight will penetrate a few centimeters into the rock crust, but the energy quickly gets re-radiated out. Energy doesn't tend to work its way in towards the center of a planet any more than water tends to freeze into ice cubes while sitting in your glass. The energy is always trying to leak out and evenly distribute itself throughout space. So once the ground rock is absorbing sunlight, it's quickly re-radiating it back out into space. So sunlight does not have the ability to affect internal temperature, at least not on a terrestrial planet. And even on the icier moons, it's not too much either. So, but I just wanted to correct you, Lucas, because remember that Venus is actually hotter than Mercury by a small amount. I think the average temperature in Kelvin is 740 Kelvin, or maybe that's 480 Celsius. Venus is a bit hotter than Mercury, especially considering that Mercury has two temperatures. So can you rephrase your question in such a way where you don't say that Mercury is the hottest planet?
So I would ask, does being closer to the sun have any effect on internal temperature of a planet?
No.
Which you're
really.
saying no.
The interior of Jupiter is warmer than the interior of Earth.
So Mercury's just like on a slow death march.
I mean, all planets are, but Mercury's kind of already dead. Mercury's already marched itself to death, more or less. It's more like Earth and Venus and Mars are on a well, Venus just sucks, but Mars is sort of in the process of dying. The only cool planet is Earth. That's the moral of the story, okay? No, I'm sorry. The only geologically active planet, well, all right, that's not true. Mars has wind erosion, so Mars is geologically active. And Venus has volcanism, so Venus is geologically active. But planets do slowly march towards death. They cool out over time, and eventually, but if a planet like Earth, I don't think will ever completely lose its atmosphere. It's got enough gravity where there'll always be some gas floating around. The atmosphere may evolve over time, especially if volcanoes crust over. I don't know. I hope that answered your question, but
Yeah, it did.
Oh, okay. In any case, rotation rate affects two things. The first, the thing that everyone forgets about, is your magnetic field. And I tried to impress upon you in your last lecture that magnetic fields protect atmospheres. And in that sense, they are extremely important. The other thing rotation rate affects is wind erosion and circulation. Now, I didn't have a chance to go completely bonkers on this last time. I wish I did, actually. But just to make a passing mention of it, because it's going to come up in our office hours today, There's a difference between circulation, atmospheric circulation on Earth and Venus that's directly tied to rotation or lack thereof it. Now, normally I would take some notes on this, but in the interest of covering much ground today, I'm just going to kind of talk you through it. Let me introduce you to a concept in atmospheric science called the Hadley cell. Hadley cells are basically giant convection cells that circulate in the atmosphere of a planet. Now, unfortunately, the illustrators who were in charge of drawing for this book made a big tactical mistake. They put Earth underneath this diagram, but I wish they hadn't. In fact, I need to go into Photoshop and scratch out Earth and put Venus in its place. This is very much what the atmospheric circulation of the planet Venus looks like. Of course, if you're relatively perpendicular to the ecliptic, our axis tilt is 20 degrees, Venus's is close to 0 degrees, then you'll get more direct sunlight, more perpendicular sunlight at your equator than you do at the poles, where it comes in at a glancing angle, right? You learned about this during our seasons lecture. And that means you get more planetary warming along the equator, you heat up your atmosphere, and that creates convection. Bubbles of hot air rise and begin to circulate up towards the poles. Cooler air circulates along the surface towards the equator. On Venus, which has no rotation, the planet's circulation is divided up into basically one giant Hadley cell. You get a circulation cell in the northern hemisphere and a circulation cell in the southern hemisphere. And this circulation is so effective at atmospheric mixing that Venus maintains the same temperature along its equator as it does at the North Pole. And that's pretty weird if you think about it in comparison to Earth. The North Pole is not the same temperature as Ecuador, but it is on Venus. The reason why Earth does not have one giant Hadley cell is because rotation breaks up your circulation through a process in physics called the Coriolis force. The Coriolis force is a twisting force that develops in rotating coordinate systems. And you know, normally you learn about the Coriolis force in your physics class. Let me exit out of here. On Earth, the active twisting Coriolis forces, which I have a lecture on that, but I'm skipping that. It splits Earth's Hadley cells into a set of triple Hadley cells. Now, this is sort of another unique feature of Earth's atmosphere here. The twisting of our atmosphere as Earth rotates rapidly sets us up with these three little Hadley cells, which are almost like little mini refrigeration units. You get a Hadley cell along the equatorial regions. You get a ferrule cell along temperate zones. And then there's a polar cell up near the poles of Earth. And this is how we get our three different sort of climates on Earth. We have tropics, we have temperate zones, and we have polar regions. It also protects Earth from climate change in a way, because Earth requires liquid water to maintain plate tectonics. And if you have these three different little refrigeration units on Earth, you'll always make sure that there's some water somewhere on Earth. If Earth goes into a global snowball ice age, and the ice caps sort of march their way down the continents here, you'll always have some areas that are warm enough along the equator for liquid water to exist. And likewise, if we overheat our planet in the future, the hope is that even if you boiled away part of your oceans into steam, even if you melted your ice caps, it would still be cool enough near the North Poles to maintain some liquid water. And water, as you learned in your last lecture, traps carbon. So rotation rate affects a planet in complex ways. On Earth, it helps maintain climate stability by splitting our circulation into these triple Hadley cells. It's also responsible for wind and weather patterns, and I had some yapping to do about that, but I think I got to skip it. Now, one of the things we learn about the Coriolis force is that the Coriolis force is proportional to rotation. the faster your record player rotates, the stronger the twisting force as you move from the center to the edge or from the edge to the center. Earth rotates in about 24 hours. Venus doesn't rotate, and it has one big Hadley cell. Earth rotates in 24 hours. It has 1, 2, 3 Hadley cells. What would happen if Earth rotated faster? Say it had a period of 11 hours, like the planet Jupiter. Can you predict what would happen to these Hadley cells?
Would there be 9 of them?
Something like that, yeah. And with that, Jace, I give you the planet Jupiter. This is how Jupiter develops its beautiful banded stripe layers. Do you see all these cool stripes on Jupiter? Those are all Hadley cells that sit at slightly different altitudes in the atmosphere of Jupiter. The fact that Jupiter is this massive planet that's rotating in an 11-hour period, which is half of Earth's rotation rate, creates intense Coriolis forces, which creates many, many layers of Hadley cells. And you can see there's close to 9, Jace. There's 1, 2, 3, 4. It's kind of hard to count them in a picture that's this high resolution. But certain pictures of Jupiter, you can count the layers. And you seem to be getting about somewhere close to 9 per hemisphere or so. So that was a pretty good prediction. Okay, so we're going to be discussing the Jovian systems today. That was a bit of a long preamble, but also a summary of everything we learned in the terrestrial zone. And it's going to turn out that when you cross the asteroid belt and you enter into Jovian territories, a lot of the geology that we saw in the inner solar system shows up again in a bizarro upside down form because the Jovian worlds introduce a new player into the solar system. Whereas before, our planets were strictly made of metal in the core and rock at the surface, now we are going to be introducing ices, not only water ice, but other types of volatiles like methane, ammonia, and I suppose even carbon dioxide might be considered a sort of volatile. It's similar to ice. And all right, first of all, do you guys know the names of each of these planets? I want to make sure that.
Uranus, Neptune, and Saturn, and
What color is Uranus?
it's the greener one.
Yeah, this is Uranus, okay? And this is Neptune, okay. So Neptune's blue, Uranus is green, Saturn's got the rings and some haze that's yellow. Jupiter has the intense stripes. All of these planets have lots of moons. And I might change you a bit on there's a couple of cool parts of the planets themselves I want to talk about, but I definitely want to get to pictures of moons before this class ends, or I'm going to be sad. But first, a word from our sponsor, hydrogen ices, okay? We need to do a little lesson on chemistry before we exit our asteroid belt. So one of the fundamental properties that build up planets and moons in the outer solar system are a set of volatiles called hydrogen ices. Hydrogen ices, which are sometimes called volatiles, share some common attributes. They have low sublimation or evaporation points, and they can very quickly go from an ice phase to a gas phase in space, and they can easily melt. If you think about water, water has a range of temperature under atmospheric pressure of 0 to 100 Celsius. In outer space, I think the sublimation point of ice is 160 Kelvin, which is pretty cold if you think about it. That's like a bit warmer than the dark side of Mercury. And hydrogen ices include, of course, our friend water, which is H2O. That's an oxygen connected to 2 little hydrogens, right? And as you know, clouds of water tend to be white in a vapor form or transparent. white usually. Another important player is ammonia, which has the chemical symbol NH3. And geometrically, it looks like a big nitrogen with 3 little hydrogens connected in a pyramid shape, a tetrahedronal shape, I suppose you'd say. And ammonia clouds tend to be yellow when we see them on Jovian planets. Next, we have methane. Methane's chemical symbol is carbon with 4 hydrogens attached to it. And it kind of looks like a boomerang here, okay? So it's, well, 4-sided boomerang. It's got a carbon with 4 hydrogens stuck to it. It tends to make blue clouds. Now, I hope you guys are understanding why we call these things hydrogen ices. They feature a prominent atom in our solar system, like carbon, nitrogen, or oxygen, which are some of the main ingredients that come from stars, with a bunch of hydrogen dingleberries stuck to them. And they all kind of behave chemically similar. They go from ice to gas relatively quick in the vacuum of space. We also should mention some bit players that you're about to see, some players that are still volatiles, but are on the edge of hydrogen ices. One that we see in the cloud tops of Jupiter, and we see in a few other places, they're responsible for the red clouds, is ammonium hydrosulfide. Okay, my chemistry is not as good as some of our conference attenders here, but I believe it's NH3SH. Oh, geez, guys. Ammonium hydrosulfide. I lost it. Let's cheat. Unless anyone out there in the studio audience knows the chemical composition of ammonium hydrosulfide, we're going to cheat. By the way, hydrosulfide. Another fun factoid is I think ammonium hydrosulfide is the chemical ingredient that makes stink bombs smelly. So there are massive stink bomb clouds. How did I do? How did I do on my guess? Oh, NH4HS. Whatever. Okay, NH4SH. Well, I tried, okay? I don't know if it matters whether the S or the H comes first, but ammonium hydrosulfide, whatever this stuff is, the stink bomb stuff, is responsible for the red clouds that we see in Jupiter's atmosphere, and is responsible for some coloration on the ices of planets. I want to mention a bit player in here. It's definitely not a hydrogen ice because it doesn't have hydrogen, but we've already seen quite a bit of this on the surface of Mars. Carbon dioxide shows up a lot in the atmospheres and ices of planets. Carbon dioxide. You guys know what color carbon dioxide vapors are? Ever seen dry ice before? Let's look at a picture.
Like
Ever
white.
make dry ice cream? What'd you say, Jace?
It's white,
Yeah.
like water.
Yeah, like water clouds. Mars's ice caps are a pretty close mixture of water and CO2. CO2, of course, sublimates even at atmospheric pressure. Here you can see sublimation in action, going directly from the ice phase to the gas phase. Helpful for cool fog machine-like effects. What was awesome? Dry ice cream? Dry ice cream? All right, so this is responsible for white clouds. So these are some of the, this is
I have
a
a question.
microchemistry lecture. These are some of the ices that are going to make the outer solar system different. Now, in space, the ice gas sublimation point of water is 160 Kelvin. And it being our last lecture and all, it's maybe important that we do an interesting sample problem that will illuminate some aspect of the solar system. I'm just going to give you guys a second to catch up to that, because it looks like Laura's still writing. Oh, you're good? Kayla, can I erase, or are you still copying? How about the rest of you guys? How about the trolls? Yep, okay. Let's talk about the formation of terrestrial versus Jovian planets. Have you ever wondered why the, where are we here? Where's our solar system lecture? Why is it that all the terrestrials formed close to the sun, and, oh, Jace, question.
I just wanted to ask, how can we tell the difference between water clouds and CO2 clouds?
Spectroscopy, or you could taste it. But probably spectroscopy would be the answer to that question. I don't know if there's a way to tell by eye, because I haven't spent enough time looking at the two, but spectroscopy is usually the way you do that.
I have a quick question, just one more stupid question based on the slide you're showing.
Yeah.
I read somewhere that, like, it's not only Saturn that has rings, but Saturn's always the one that's, like, depicted with rings.
It's what? Depicted with rings.
Saturn's not the only planet with, like, a ring system, but it's the only one that's ever shown with one, like in a rendering.
Right. So there's an interesting reason for this. While all the Jovian planets have rings, the other ring systems are quite thin. And there's a reason for this. In the Jovian ring system, ice particles actually undergo, okay, so first of all, I'm assuming you know some things that you guys might not know. Let's just jump ahead in time to my pictures, beautiful pictures from the Cassini mission of Saturn's ring systems. Of course, the ring systems look smooth like a record on a record player, but they're actually comprised of thousands and thousands of bits of chunky ice. Each one may be similar to the size of a compact car up to school bus sizes. Now, in the asteroid belt, where we have giant chunks of rock, the interparticle separation between asteroids, the mean free path, if you will, is so great that asteroids never collide with one another. This is not true for rings of Saturn and rings of other Jovian planets. These guys are close enough where they suffer collisions maybe once every 5 hours. So a typical ring particle gets bashed by another ring, a few times a day, once every 5 hours. And the effect of these constant smashings and bashings over geological timescales is to sort of grind the rings of the planets up into dust. Now, there's an interesting thing about scattering light off of dust grains versus ice particles. And here's a cute little slide that tries to explain the difference. If you have a large chunk of ice that's the size of a car, you're in a regime called geometrical scattering, where photons that come in are much smaller than your ice chunk, so they backscatter towards your eyeball on Earth. Now, that's good for Saturn's ice particles because they're big, and that means we can see the rings even through a small telescope like the CCRI 16-inch telescope. But as you grind yourself up into smaller dust grains of micron size or smaller, you enter a different scattering regime where instead of photons being able to just backscatter off, they kind of forward scatter and they skip off the grains forwardly the way you would skip a stone off of water. I think that might be me scattering is the regime, but don't quote me on that. There's 3 different scattering regimes. And what that means, if I cut through the technical garbly-gook, is that you can't really see Jupiter's rings from Earth because Jupiter's rings have effectively ground themselves up into dust. The way you can see Jupiter's rings is to take a trip there like they did with the Galileo space mission and get behind the planet as it passes in front of the sun, so you can see those dust grains. You can see sunlight scattering off of those tiny dust grains, and that gave us one of our most iconic images of the Galileo spacecraft mission. Here you can see the spacecraft behind the planet Jupiter, and now you can suddenly see Jupiter's rings revealed as they are forward scattered, excuse me, off of those tiny dust grains. And similar arguments are true for Uranus and Neptune. Their ring systems are basically ground to dust. So, Lucas, we have another planetary mystery here. If all the Jovian planets kind of formed in the outer solar system together, and if the physics is the same, why do Saturn's rings look so beautiful and prominent today, but Jupiter, Uranus, and Neptune have ground themselves up into dust? Basically, what's weird is not that the other planets don't show rings. What's weird is that Saturn's rings look so potent today when they should have just ground themselves into smithereens eons ago. Now, because if I don't answer this question now, I'll probably never come back to it. I'm going to tell you the answer to it because otherwise it'll be forever gnawing at your brains as you sleep at night. The real secret to why Saturn's rings have persisted has to do once again with moons. If you look at the moons of the outer solar system, there's kind of three different classes. There are big moons, which are almost the size of our moon or Mercury, slide 59. And Jupiter's famous for just having some big whoppers. It's got the 4 Galilean moons, Io, Europa, Ganymede, and Callisto. Saturn's got a big whopper of a moon called Titan, and it's got some medium moons and some small moons. And the moons of Uranus and Neptune are kind of small, maybe with the exception of Triton. I'm going to go through all these in a few minutes. But the real secret to Saturn's moons is its plethora of medium-sized moons. And I will define what I mean by a medium-sized moon later. Here's the idea. Most of the moons in the outer solar system are not simply made of rock or metal, but they're mostly made of ices. And even though we're quite far from the sun, we're still at temperatures where some of these ices can melt or sublimate. And when they do, they can create giant geysers of water that shoot out into the outer space environment. So one of the cool results that we got back from our Cassini space mission are the Enceladus, a moon of Saturn, shoots out these jets of water into the Saturnian environment. So we flew by this lovely moon, Enceladus. It's covered in water ice, some of which you can see is partially melted or recently underwent some kind of interesting tectonic structures. Notice one side of the moon is cratered, but the other side is quite smooth. And when we flew past this moon, we basically saw something that looks like this. We saw these jets of water ice. Unfortunately, this is a very talented weed-smoking artist illustration, but the picture looks actually identical to this. So we see them shooting off these jets of water vapor into the outer space environment. That stuff's going to solidify and crust over into ice chunks. The other thing has to do with tidal forces. Some of these moons occasionally wander in close to Saturn. And when they do, Saturn is just chewing apart and ripping its moons apart into ice chunks. We see that in the so-called gap moons. Believe it or not, we actually find moons buried inside the rings. One that's going to show up in your office hours today, we're going to do a kind of gnarly problem on these two legendary Shepard moons or gap moons called Prometheus and Pandora, slide 140. And here you can see an up-close image of these small-sized icy moons using their gravitational influence to shepherd the icy particles of the F ring into a narrow sort of clump there. So there be moons in them rings, and occasionally tidal forces can separate them and strip them apart. That's how Saturn maintains its rings. So cool question, Lucas, and way to get me the hell off track, okay? Way to prevent me from doing a math problem with you. I can see what happened there. Okay, so I want to talk to you guys about ices, and I want to talk to you about a vocabulary word called planetesimals. Let's talk about how planets form. And to do this, I'm going to go to a slightly different lecture show here, one on the formation of the solar system. Let's take our minds back 4.6 billion years ago to the formation of our solar system, when we were nothing more than a proto-solar nebula with a protostar like sun in the center of our solar system and a giant disk of dusty debris stretching out towards the orbit of Pluto and beyond. Over time, planets begin to assemble in form in this proto-solar nebula. And in one kind of cool illustration I have here, I can show it to you here. You can see a little illustration of a planet forming within the proto-solar nebula. Now, the usual thing that you surmise when you imagine a planet forming in the proto-solar nebula, if you ever do such a thing, is you imagine that this material is spinning too fast, has too much angular momentum, and cannot fall into the parent star, and eventually gravity begins to assemble it into a planet. But that can't be the entire story, and that's because the original pieces of solid material in this nebula are not much bigger than a grain of sand or maybe even microns in sizes. Now, I suppose these two markers in my hand have mass, and that means they have a gravitational interaction, but I cannot feel the gravitational attraction of these two markers if I hold them in my hand. Whatever it is such a microscopic, minuscule amount of newtons that for all intents and purposes, there is no attractive force between these markers. This isn't really working. I can rest them safely on my laptop here, and I'm not in danger of these things clicking together. So it makes you realize that the initial little lumps of rock themselves couldn't have much gravity. And gravity probably isn't the mechanism that originally seeds the planets or forms them. It's actually random collisions and static forces, static cling, that kind of clumps these things together. The original seeds that form planets are known as planetesimals in planetary science. And let me see if I can, so here's a little, oops, can I go back a slide or forward a slide? This is a little concept of how planetesimals must eventually arrange themselves. They start off as mere bits of grains of sand that undergo orbital collisions. Weak static cling sort of clings the particles together. And over time, more collisions clump them into bigger and bigger lumps, maybe the size of an asteroid. And eventually, if they swell large enough, they will become gravitationally influencing to their surrounding particles and build up the mass to make a planet. And so we call these things planetesimals. I want to introduce you guys to a concept called the frost line. If you could imagine forming an early planetesimal, the compositions of planetesimals would be different depending on whether you are close to your sun or far from your sun. As we know, there is a temperature gradient in the solar system. The closer you are to the sun, the warmer you are. Near the sun, if you were like Mercury or Venus or Earth, your planetesimals, the things that seeded your planets, would resemble something like an asteroid. They'd be mostly made of rock and metal. That's because water would be in a gaseous phase and could not contribute to collisions or static cling. But as you get farther from the sun, the water and the volatiles, the ammonia, oh, even diatomic nitrogen, I should have put on that list. Even nitrogen, which can turn to ice far from our solar system, these would be in a solid grain form, and they could contribute to collisions and form part of that static cling that builds up a planetesimal. This is why Jovians swelled to such immense sizes. It's because their composition had extra mass in the form of ice, rock, metal, and ice. The idea is that there's this concept called the frost line, And there are different frost lines for different materials in our solar system. But for the case of water, there is some critical distance at which your Jovian planetesimals would have gone from rock to ice. And believe it or not, we can calculate this frost line using a formula that I introduced to you in our last lecture. That formula is called the no greenhouse temperature. Okay. Let's find the frost line. We know that the temperature of any lump of rock, metal, or ice will be dependent upon two factors: its distance from the sun and its albedo. What the hell is the albedo, class? Who's a good student that knows what an albedo is? A stands for albedo or albedo.
Reflectivity.
Reflectivity, that's right. Jace, suppose we wanted to consider some solar system ice. We know that the temperature at which it sublimates is 160 Kelvin. What would you say is a reasonable albedo for primordial ice? Remember that your options are 0 through 1, or 0% to 100%.
0 is white, right?
No, 0, it's reflectivity. So 0 means
Okay.
I reflect 0%. 0 is black and 1 is white.
So maybe it would be high, like maybe 0.8.
I think in our slide system last time, come on, baby. I had pictures of albedos here. What did my slide last time suggest for ice?
80 to 95%.
Yeah, except guess what, Jace? That would be not a very good guess. I mean, that's what I would have guessed naively too. But here, I'm tricking you. I was hoping you'd say that, Jace. That's 80% was a very reasonable guess, it turns out, okay? But here's the problem, Jace. This is fresh snow, like pure as the driven snow. And nothing in our solar system is clean. I want to show you guys a couple of pictures from planetary science here. There's a famous spacecraft named the Rosetta spacecraft mission, whose purpose was to travel to a comet named 67P Gerasimenko. It's a rubber ducky-shaped comet. And the Rosetta spacecraft. I might have mentioned this before. One of the cool things about this mission is that they designed a washing machine-sized probe which fired down and landed on the surface of this comet. So the comet was on, I'm sorry, the comet that they were interested in studying was 67P Gerasimenko. Okay, so I botched that a little bit. Anyways, the mission was to land on this guy. And it turns out that the nuclei of comets are made of primordial ice. Ice that's quite similar to the ice that you would find in a Jovian Planetesimal. And these pictures are so super high resolution. Before this spacecraft approached the comet, we had never seen such an up-close picture of the nucleus of a comet. Normally, because you just see them on the sky and they're surrounded by a coma of water vapor. Actually, if you guys look close in this image, can you see those jets of water vapor shooting off? These are jets of sublimated ice just turning into vapor. It's blasting off the surface and ejecting little pebbles and rock. Look how filthy this snow is. It's jet black. This is dirty snow, like the snow that you find under car tires in the city during the winter time. And while you would think that ice and snow would be 80 to 90% reflective, this ice has been whipping around the solar system, collecting bits of cosmic nanodust and other associated grit that's flying around. When we find primordial ice in our solar system, it's nasty, dirty, dark ice. I think the typical albedo of comets is like 5%. In fact, let's look at the, sorry guys. Let's click on Comet 67P Churyumov-Gerasimenko, say that 5 times fast, and let's see if they list its albedo here in its list of stats. Ha! 6%. Okay. Anyways, you get my point, right, Jace? Your first guess is not always your best guess. Let's use 5%, although 6% would have been just fine. Okay, we're going to have to do some maths here. 160 Kelvin is equal to 280 Kelvin times the 4th root of 1 minus 0.05 divided by the distance. We want to find the distance because the distance is the frost line. This will tell me where ice will go into a gas phase. Peace, Lucas. Okay, I'm going to do 160 over 280. I'm going to raise it to the 4th power, and that's going to equal 95% over d squared. Now I'm going to solve for the distance. The distance is the square root of 95% divided by 160 over 280 to the 4th power. It wouldn't be an astronomy class if you didn't have to punch and crunch. So do your duty. Do your civic duty. Can I get some iced tea with ice? Thank you. All this talk of ice is building up a fierce thirst in your instructor here. Iced tea with ice, if I could. I need the drugs.
Is it 6,000?
Nah.
No.
Well, if it is, I'll be a camel. What?
I slipped on the banana peel.
Okay, wait, hold on. Oh, you slipped? Yeah, do you remember that?
Yeah.
Do you remember that lesson?
Yep.
That's great. Okay, let's do it together, shall we? 0.95 divided by, open parentheses, 160 divided by 280, close parentheses, raised to the power of 4 equals shift square root. What do you get? Thank you.
3.
Yeah, and what are the units of that 3, Jace?
Kilometers?
Hell no.
Are we finding a distance?
We are. This is not MKS units formula.
AU.
Beautiful. Whoever said that, thank you. This is very interesting. Huh. This is not random. Why would I find 3 kilometers to be an interesting result for our frost line? Do you know, Tony? Or are you just laughing that I would find 3 astronomical units interesting?
I'm laughing because you accidentally said 3 kilometers.
Wait, oh, Jesus. All right, that was the whiskey talking right there, okay? So not 3 kilometers, 3 astronomical units. Why is that number not random? Can anyone think, what's at 3 astronomical units from the sun?
Is that where the asteroid belt thing is?
Now you're with me. In fact, it's the edge of the asteroid belt. The asteroid belt spans a range of 2 to 3 astronomical units, but it's so curious that as soon as the asteroid belt ends, that's where your icy particles begin, right? Do I have a picture showing distance? Hold on. sometimes you can get a picture of the asteroid belt kind of mapped out in terms of distance, a sort of useful information graphic. Ah, here we go. That's the puppy I'm looking for. So guys, it makes perfect sense that the Jovians would begin just outside the asteroid belt, because as you can see in this picture here, right at 3 astronomical units, that's the edge. There's your, wait, hold on. There's your frost line right there, right? Sorry, I was trying to find a more symbolic choice. 3 astronomical units, there you go. Right at the edge of the asteroid belt. Interior to this line, you form planets from rock and metal. Outside this line, you find planets made of ices, rock and metal. Okay, cool. So, what do we know about Jovians? Let's talk about their composition. If you remember the composition of the sun, well, you're in pretty good shape to learn the composition of a typical Jovian planet. For our intents and purposes, we're going to say the compositions of all the Jovians are the same. They are hydrogen gas, or molecular hydrogen, and 70% by mass, just like our sun. Helium, sometimes in the form of gas, 28%. And now our 2% metals, I'm going to segregate into basically different, I'm not going to just leave it at hydrogen ices. I'm just going to say ices, not just water, but various types of ices, 1%. And then at a less than 1% level, somewhere in the core, rock and metal. So there's your typical Jovian composition right there. It turns out that Uranus and Neptune have slightly higher percentages of ice in their interior. That's why it's become fashionable to refer to them as the ice giants. But I'm going to leave that small point aside. Now, it turns out that we have a pretty good sense of what the cloud layers of Jupiter are comprised of chemically, because we actually sent a probe into a suicide mission down into the atmosphere of Jupiter. And I want to share this with you guys here. Oops, sorry. Share screen, share it. And let's take a look at the Galileo spacecraft. In the 90s, we launched okay, first of all, let's just talk turkey. Before the Galileo spacecraft came around, our only knowledge of the Jovian planets came from the Voyager spacecraft. So let's look at the Voyager orbits. A couple of these slides have dates affixed to them. Here's a little sort of time lapse of the dates that Voyager 1 and 2 visited the outer worlds. Before Voyager 1 and 2 in the 70s and 80s, our only knowledge of the Jovian planets was just looking through small telescopes like the CCRI telescope. We could see the rings, we could see that there was some stripes there, but we really hadn't gotten up close to take a look at them. And the launch dates for Voyager 1 and 2 were around 77, and they made what's known as the Grand Tour of the planets. Voyager 1 visited Jupiter and Saturn and then left the solar system. Miraculously, Voyager 2 actually did a flyby of all 4 Jovian planets and is now also currently on a trajectory leaving our solar system. And if you think about camera technology in the 70s and the 80s, it was much cruder than the high-resolution digital cameras we have today. So it was a wonderful gift to be able to send probes both to Jupiter and Saturn in the modern era. By the way, you're going to notice that when I go from pictures of Jupiter and Saturn to pictures of Uranus and Neptune, the quality gets significantly reduced because I'm still using Voyager spacecraft images of Uranus and Neptune. We have not had a modern flyby mission there. So the Galileo spacecraft was launched, I think, in the 90s. I just want to show you a picture of it in the clean room because I want to inspire you to work in an office that looks like this instead of Allstate Insurance, okay? I want you in the future to be punching into your office here with these guys and working on these machines. And can you guys see this probe they have here? This was attached to the mothership, and this probe here went on a kamikaze journey down into the cloud tops of Jupiter, sampling temperatures and chemical compositions. So I think in my slideshow here, let me exit out of this. Hold on, let me get rid of that. Oops, I'm too fast for the machines here. Let's get rid of you. And let's minimize you. And let's exit out of you. Sorry, there's too many damn slides here. Okay, so let me get over to the atmospheric profiles of the Jovians for a second. Okay, so we flew out in the 90s in zeros to Jupiter on the Galileo spacecraft, and we dropped a probe into a fiery heat death down into the atmospheric layers of Jupiter. Now, you will remember that one of the key lessons from our atmospheres chapter was that we constructed this graph known as the temperature scale height, a plot of temperature as a function of depth in the atmosphere, and that's sort of how we define the layers of a planetary atmosphere. Let's take a little peeksy-weeksy at the temperature scale height of Jupiter and what we learned from the Galileo probe. Get this tucked away here. Okay, so first of all, one good question that we might ask ourselves is, how does one define the layer, how does one define the surface of Jupiter when there is no solid surface? You just sink deeper and deeper into the pea soup, the gas becomes warmer, denser, and hotter, and eventually probably almost becomes like a liquid, it's so dense. You can see that what they did in their temperature scale height diagram is they defined 0 kilometers to be the top of the cloud layers, which they then defined as the troposphere. So the troposphere is where temperatures just begin to rise. And one of the key interesting discoveries of the Galileo spacecraft is that Jupiter actually has a stratospheric bump like Earth. Students, what was the cause of Earth's stratospheric bump? Do you remember? That's something I'd like you to know. How did Earth get a stratosphere? Anyone? Stratospheric bump. 10 words or less. Go.
It's heated by the UV light.
Interacting with?
Ozone.
Exactly. Jace, that's what's happening here? Is ultraviolet light interacting with ozone in Jupiter's atmosphere?
I don't know.
What fraction of Earth's atmosphere does oxygen comprise? Or compose? Whatever. You understand what I'm saying. What percentage of this gas is oxygen on Earth? Feel free to chime in, Laura and Tony, and save him. Kayla?
Is it 21%?
21%, that's right. What fraction of Jupiter's atmosphere is oxygen?
Only 1%.
0 fucking percent. There is no oxygen in Jupiter's atmosphere. Oxygen is an anomaly. Wait, sorry, Tony. Look, Tony, 1% was ices, right? Diatomic oxygen is not an ice. It's a volatile, explosive gas. Oxygen is good for blowing things up, and that's pretty much it, okay? Including your cells. Okay. I'm just trying to make a point here, guys. Sorry, I'm always trying to make a point. And my point is, we don't really know, or maybe in some esoteric paper there's some suggestions, but this is a mystery of planetary science, I believe, to this day. We believe that probably it's a combination of ultraviolet photons interacting with some trace chemical, but I don't know if we know what the trace chemical is. One thing's for sure, it ain't ozone because there's no oxygen in Jupiter's atmosphere. This is a mystery. Let's look at some other interesting things. There are 3 different cloud layers. There's a layer of yellow clouds. These are, once we get into the troposphere, the upper layer of clouds is yellow, and they're made of pure ammonia. Then there's another layer of clouds, which are red, and these are made of ammonium hydrosulfide, stink bomb material. And then sitting underneath that are clouds of water. And this is interesting because when you look at the layers of Jupiter's atmosphere, a picture doesn't really do justice to the depths that these clouds lie within the atmosphere. Let's see if I can go back here. It kind of looks like all the cloud layers are swirling around together, but they actually lie at much different depths inside the Jovian system. I mean, imagine what it would be like if you could fly your own spacecraft through the clouds of Jupiter on a joyride. There'd probably be all kinds of wacky storm systems, and you might be able to fly underneath a layer of ammonia clouds that were snowing ammonia flakes down onto sheets of ammonia hydrosulfide, which were then dropping into rain droplets onto water clouds. On Earth, we've got one type of cloud, water clouds, and just think of all the crazy storms you've lived through in your life. On Jupiter, storm systems must be triply complex because of all these cloud layers interacting with each other. Here's a picture of Jupiter in the infrared, and you'll notice some interesting things. The red clouds seem to be warmer in the infrared, showing that they lie at deeper depths than the colder, cooler temperatures of the ammonia clouds. Although one of the weird mysteries of the Great Red Spot is that it's a red spot made of ammonium hydrosulfide, but it shows up as cool in this infrared image. That tells us that unlike low-pressure storms, unlike low-pressure storm systems, this storm layer lies higher up in Jupiter's atmosphere. You know, the Great Red Spot has persisted for hundreds of years. And if you think about it, on Earth, storm systems are usually broken up by traveling over land. On Jupiter, there's no land. And so these storms can just circulate around for hundreds and hundreds of years. Oh, Kayla, you raised your hand. What are you thinking? I wasn't looking at you there.
How can there be a layer of water clouds if there's no oxygen?
Because I'm not being clear about what I mean about no oxygen. When I say no oxygen, I mean no diatomic oxygen, O2. Yes, oxygen is connected to hydrogens, but for a moment, and don't let this, ruin my reputation, but for a moment I was thinking like a chemist. Chemists tend to think that it's oxygen diatomic it's a different molecule, so they're not the same thing. And sure enough, they behave quite. One would never say that water and oxygen behave the same, but you're thinking like an astronomer who just thinks of the entire universe as pulverized into atoms. And what type of nuclear fusion did this produce, right? But I meant diatomic oxygen, O2, right? Not the same thing as water. Okay, so I don't know. By the way, I want to say one thing about the Great Red Spot. We always, when we imaged Neptune for the first time in the in the Voyager missions, let me go back to that slide again, actually. Where are we here? Let me go to my first intro picture of Neptune. One of the things the Voyager 2 mission discovered when it flew past Neptune is that it seemed to have a similar storm system, which they dubbed the Great Dark Spot. Since Voyager passed by in the 80s, subsequent imaging with the Hubble Space Telescope has determined that the Great Dark Spot has disappeared, and it's been broken up or dissipated, which makes people wonder if it's possible for the Great Red Spot to someday disappear. The Great Red Spot's been around on Jupiter for hundreds of years. I mean, I don't think Galileo could resolve it with his telescope, but we quickly started building telescopes that were capable of resolving this thing. While we've wondered for years whether maybe the time scale, how long ago was Galileo, right? Galileo built his telescope in the 1600s. So we've only been looking at Jupiter for 300-400 years. Perhaps these things have a time scale that's 1,000 years. We wouldn't even know it yet. Subsequent imaging has determined that rather than having the Great Red Spot disappear, we now have a new Great Red Spot known as Great Red Spot Junior. Oh my gosh. I realized I'm running out of time. I just looked at the clock and I'm getting really depressed. Okay. This calls for different measures. I'm not showing you a picture of Great Red Spot Junior because I'm getting very close to out of time. I want to show you a couple of important things here. This is what we believe the interior of Jupiter looks like. This is what it would be like if we could go deeper and deeper into the heart of Jupiter. Slide 21. At some point, Jupiter, unlike a star, becomes denser, hotter, but the pressure actually rises quite fast inside the interior. In our sun, the central nugget is basically a nuclear fusion bomb, and that makes temperatures berserkly high. But Jupiter is much colder than the sun, and it doesn't have enough mass to ignite nuclear fusion. But the pressure continues to rise as you go deeper and deeper. And that means somewhere underneath this layer of gaseous hydrogen, the pressures probably increase enough where we can condense our hydrogen from a gaseous phase into a liquid phase. Now, there's not many places in our universe where we could find liquid hydrogen. In fact, the interiors of a Jovian planet are probably one of the only places. Sorry, I'm trying to get my pencil tool out here. At some point, hydrogen must condense into a liquid, and then even more preposterous, once the pressures go above 2 million bars, we've calculated that the hydrogen must then condense into a metallic form. Hydrogen in metallic form is a metal. Although, I gotta tell you, I don't believe we can compress hydrogen into a liquid or metal form in any terrestrial laboratory. You know, when I worked in the infrared wing at the Stewart Observatory in Arizona, we used to use liquid nitrogen to cool the infrared chips before we tested them. But there was no liquid hydrogen. Liquid nitrogen, I think, condenses at, gosh, what is it? It's 30 or 40 Kelvin, something like that. But I don't think there's any temperature at atmospheric pressure at which you could take the most volatile gas on the periodic table and condense it into a solid. And it gets me thinking, why do we call these things gas giants anyways? The vast majority of the interior of Jupiter is like a giant rotating ball of metal. And for this reason, the Jovians have very powerful magnetic fields. Okay, you know what time have we got here? Because I've definitely screwed this day up. Well, I didn't screw the day up. It just takes time to talk about these things. We are approaching the end of our lecture and the end of our course. I did not get to Jovian Moons. I'm going to cry later on because of this. I'm very sad about that, but you know, blame COVID-19 and the extra week of spring break for that. Okay, let's talk plan. We're going to do some homework today. Yes. Going to do some homework on planetary atmospheres. That's chapter 10. You guys will notice in your blackboard for the course that I have set up a homework assignment for today, and I've included the questions. This is homework 10, chapter 10. These are the questions we'll be doing, and you can download the You can download the actual page of questions from your book here so that you can read along with me. I guess we'll take our usual 5 or 10 minute iced tea break, and then we'll begin at 1 o'clock. Everyone agree with the plan? Okay. Oh, you know what I screwed up on, guys? I was supposed to give you guys a chance to evaluate me and evaluate this course. And I enjoyed that because that's a nice chance to hear back from you guys about how you thought the course went. I think I was supposed to do that digitally, and I honestly completely forgot about it until right now. So maybe I'll kind of take a look and see if I can figure out, I'll make an emergency telephone call and see if I can figure out how to let you do that. That will take some time on your part. Maybe after the office hour session, you can fill that out. I've got to figure out how you submit. Normally, I just do the old-fashioned paper ones. So I got to figure out how to do this in our new digital classroom here. In any case, take a break, and when we come back, we'll do our very last homework assignment, okay?